Slideshow. Yes,
All right.
yes.
Yes,
That's,
thank you,
it's
sir.
better. It's better.
It's better? Okay. All right. Very good. So this is the agenda. So we start with defining what is machine learning. Then we'll talk about some terminology of machine learning. Then take a quick look at some of the machine learning methods. And then come to the point why we want to do deep learning and what is it that machine learning cannot do. And then I'll summarize and then we'll be open for questions and answers. All right. So let's get started. So let's begin with what is machine learning. Now, there is a definition for machine learning given by Dilbert. I don't know how many of you look at Dilbert cartoons, but if you look at one over here, there is a definition of machine learning, but that's not the definition we are going to be following. Our definition is going to be machine learning is what it deals with computers and makes computers to learn using a large number of examples to make predictions or decisions. And generally, this process of learning is involved using some kind of performance measure, which we try to optimize while doing learning. So if you look at this slide and pay attention to all the words in red, those are the words that are important from a machine learning perspective. That is what machine learning is. That is without explicitly programming, using a large number of examples, and then optimizing a performance criterion while doing learning. So that's really what machine learning is. Now, I'm sure all of you have heard about machine learning. All of you have seen a large number of articles being talked about machine learning. So question is, why machine learning? And the answer to that question is the number of examples or the number of applications that are out there using machine learning. So if you look at this slide, I have outlined a large number of machine learning applications. Some of the most recent applications involve autonomous driving or self-driving vehicles, using facial recognition, building surveillance systems, in terms of Netflix, etc., doing recommendations for movies, doing recommendations for products, and things of that nature. So machine learning applications are everywhere, and that's why machine learning is gaining more and more popularity every day. Now, it's not that the machine learning applications were not thought of earlier. They've been around for a long time. People have talked about them, but the reason machine learning has become hot or very important right now is that there are three factors that have made machine learning very hot right now. One is the cheap data. That is, the data has been becoming very cheap. It has been becoming very easy to capture data, process data. Then the second factor is algorithmic economy, and I'll explain that in the next few slides. And then the use of cloud-based solutions. So there is a quote here that I'm quoting from one of the venture groups, which says that every company is now a data company capable of using machine learning in the cloud to deploy intelligent apps at a scale, thanks to three machine learning trends: data flywheel, which is basically making data cheaper, algorithm economy, and cloud-hosted intelligence. So let's look at these three factors. So here is a graph that shows data is getting cheaper. And this graph shows, of course, it's a little old graph, but it does carry the meaning that is the cost of petabytes of data as we move from 1 year to the next year has been going down and down and down, while the amount of data that is being captured and used has been going up and up and up. And just to give you an idea, Tesla, of course, I'm sure everybody is familiar with the Tesla company. So that company has 1.2 billion miles of driving data that they have captured, and that company keeps on adding another million or more bytes of data every few hours. So data is there everywhere, it is exploding, and it is also becoming cheaper to capture. Here is a recent graph, because the previous graph was a little old, so I thought, okay, let me go and grab a new graph. So this is what I found yesterday. So this graph shows how the volume of data is going to be growing, and it projects all the way up to 2024. And a small graph in the window inside is basically showing you how much Tesla is growing in terms of their data being captured via the autopilot mode. So data is there, it is growing, it is becoming cheap. Now let's come to the second factor, which we call as algorithmic economy. Now there are 4 factors for this. Number 1, anyone can turn their algorithms into scalable or shareable production-ready web services, because a lot of people are doing research, are working on their machine learning techniques. So anybody who is smart enough can come up with a new algorithm and basically come up with methods of scaling it, sharing it, and basically exploit it from a monetary point of view. And anything that can make you money obviously is going to be very attractive. So that's a reason for a lot of people getting interested in creating machine learning algorithms. Also, on the user side, people can look around and find algorithms that might be suitable for their solution. So again, that's an interesting angle right now that makes machine learning popular. Of course, all the algorithms are monetizable. That is, people can make money. Anybody who is coming up with these algorithms with certain effort can make money without establishing a big company or system. And of course, the nature of these algorithms are that they are modular. That means you can actually put them together with number of other algorithms or create a pipeline of processing, and that can help you in solving the problem. So here is again another quote: data is inherently dumb. Algorithms are where the real value lies. Algorithms define action, and people are able to create their algorithms, monetize them through apps, and in many other ways. And of course, in terms of doing implementations, people are making use of cloud-based solutions that basically helps everyone. So if you look at the trends in machine learning, people are able to create pre-trained models that they can post on the clouds, and any user can actually pay for those models and use them. So essentially what has happened is that all these factors have given rise to an ecosystem where machine learning is gaining ground every day. So with that, let's look at some of the machine learning terminology. The most important concept in machine learning is the concept of feature vectors. Because if you look at any machine learning paper, any machine learning textbook, you will find that people are talking about feature vectors. Given a collection of feature vectors, how do we build a model? So basically, let's try to understand what we mean by a feature vector. So when you build a machine learning system or a machine learning model, you will be looking at certain objects. For example, let's say that you're trying to build a model to classify different kinds of flowers. So for different kinds of flowers, you might come up with a number of features or properties. And for a given flower, what you will say is that, okay, I got these 4 properties, And as an example, let's say that the properties are sepal width, sepal length, petal width, and petal length. Now, mathematically, you can say these properties are x1, x2, x3, x4. If you line up these four properties in the form of a column vector, then that column vector is what we call as a feature vector. So in machine learning, we'll say, all right, this flower that we have here is being represented by this column vector. So a feature vector provides a mathematical representation for physical objects or for physical phenomena that we are trying to model. Here is another example. In this case, let us say you want to build a regression model for the cost of houses or house prices. So what you can say is, all right, we can differentiate different houses in terms of what is their size, what is the number of bedrooms, what is the number of floors, how old is the house, and so on. So these are the properties. And for every house, we have these numbers. So these numbers define a feature vector for a particular object. In this particular case, that object happens to be a house. So that's the concept of feature vectors in machine learning. Now, what are the different styles of machine learning? Because we are talking of looking at number of examples and then trying to build models using those examples. So the most popular style is what we call as a supervised learning. Supervised learning is very similar to learning with the help of a teacher. That is, there is somebody who has the answers to all the questions. So in supervised learning, your training data, that is a collection of examples, every example comes with its own answer. And those answers are known as labels in machine learning. So you have training data that is already labeled. And the goal of the learning is to come up with a model such that that model will produce labels for new data. So if you look at this picture, you can say, all right, here is your collection of training examples. Here is your collection of corresponding labels. From these training examples, we extract feature vectors. Along with those feature vectors and these labels, we pass on that information to a machine learning algorithm, which basically comes up with some kind of model based on this information. And once that model has been created, we can say, all right, here is our predictive model. And now if we get a new example whose label is missing, then what we'll do is we'll take that example, we'll extract feature vector from that example, and feed that feature vector to this predictive model, which will tell us what label needs to be assigned. To give a context to this whole thing, let us say that you are thinking of building a system that can differentiate between different kinds of automobiles, whether it is a Ford vehicle or it's made by GM or made by some other company. So basically, here is what you will be collecting data on those automobiles. Here you will be labeling them GM, Ford, whatever it is. Here is your system which will build a predictive model. When you deploy this model, what you will be feeding to this model is, let us say, a feature vector about a car whose manufacturer or particular model is not known. And what this predictive model will do is, it will look at that feature vector and tell us, okay, this car is made by GM and it is such and such model and so on. So that's really what we call as supervised learning. Here are some applications of supervised learning where it could be used. Supervised learning basically builds a kind of model which is known as a classification model. So supervised learning can be used for all applications where we need to perform some kind of classification. For example, you might be interested in building an application which can predict whether a customer is going to leave your service and join the service offered by your competitor. And if you can do that prediction in advance, maybe you can do something to retain that customer. So that's where the value of machine learning model lies. Or you might have a model whose job is to tag objects in pictures. In this particular case, for example, the model automatically determines that in this picture we have a dog and this is the breed of the dog and so on and so on. Or another example very close to home is whether an incoming email is a spam mail or not. Most of the systems nowadays come with the built-in spam mail filters. So basically those spam mail filters are really nothing but machine learning models that have been trained on a lot of data, and they are able to predict whether an incoming email is a spam mail or not. Supervised learning also is used for building regression models, where the objective is to predict some kind of numerical measure. So a credit card company might use a regression model to predict whether a particular customer is going to be carrying card balance or not, and if he or she is going to be carrying some balance, what is going to be the amount of that balance. Or you may want to predict how many likes will be gathered by a given Facebook posting. Or if you are in the utility business, you may want to predict what is going to be the peak load for a given day, given the weather information. So these are some of the applications of supervised learning models when you build a model which is known as the regression model. There is another style of learning, and we call that as unsupervised learning. So as the name implies, in this case, there is no teacher or no external agency to tell us what is the right answer. So in this case, the training data comes without label. That means you don't know the correct answers. And typically in unsupervised learning, the goal is to group data into different groups or categories. And this grouping is done based on similarities. So here is how the unsupervised learning takes place. Let's say here is your collection of examples, maybe news stories, maybe pictures, or maybe some other collection of feature vectors. So what we have from these examples is a collection of feature vectors that have been extracted. And these feature vectors are now passed on to an unsupervised learning method. And what this unsupervised learning method will do is, it will basically group these feature vectors into different groups, such that within each group, the feature vectors are similar to each other, while across groups, these feature vectors are not similar. So this is what unsupervised learning do. And you might ask, okay, what are the applications of unsupervised learning? So here are some applications of unsupervised learning. One is doing customer segmentation. That is, if you have a large group of customers or potential customers, and you are thinking of coming up with some kind of campaign, marketing campaign, what you want to do is you want to create not a single ad, but you want to create multiple ads so that each ad is tailored to a specific group of customers. So to achieve that goal, you need to segment or group your potential customers into 3 or 4 or 5 groups, such that each group has certain characteristics, and you can basically then target your ads based on those characteristics. Another example of unsupervised learning will be to organize a collection of documents based on their content, or make product recommendations, which is pretty common applications nowadays. If you go to YouTube or Facebook or Amazon and you click on certain item or you're thinking of buying an item, the system will also say, all right, this item is good, but you might as well take a look at some of these other items who are similar and who might be also appealing to you. So those are all applications of unsupervised learning. There is another learning style which is getting popular nowadays. It is known as reinforcement learning. So in this case, the training data again comes without labels. In this case, the learning system receives feedback from its operating environment. And the feedback is in a general sense, whether you are doing good or not pointed to any particular action. And the goal of reinforcement learning or the system is to perform better. The best example of reinforcement learning will be, when you were a kid, you were trying to learn how to ride a bike. And as you started riding a bike, you knew in the beginning you took certain actions which basically got you down from the bike, got you hurt. And as the time progressed, you realize some of those actions to be avoided. That means that was what we call as reinforcement learning. You were getting a feedback from the environment. If you fell down, that was the feedback. If you did not fall and continued to ride the bike, that was the feedback that you were doing good. So that kind of learning style is what we call as reinforcement learning. And some of the applications of reinforcement learning, for example, making robots walk, portfolio optimization, playing games, learning how to play games, and displaying ads, and a couple of other applications mentioned here. So with that, let's take a quick look at different machine learning methods. And again, we are not going to go into any details, just take a quick look to get an idea of what kind of methods are involved. And to do that, what we are going to do is we are going to walk through an example. And this example is going to be an example of flower classification. So let us say our objective is to build a classification model that is able to differentiate between two classes of flowers. And let us define those two classes of flowers. So one is known as Iris virginica, that's shown here. And another is known as Iris versicolor. And an example of this class of flower is shown here. So basically, this is what we want to do. So question is, how do we go about building this particular model? So these are the steps that I'm mentioning here, and these steps actually apply to any machine learning application that you might think of building. So the first step in this case, and in every machine learning application case, is to collect a large number of examples. In this case, since we are dealing with two types of flowers, so what we will do is we will go and collect both types of flowers. Obviously, we may not know how to differentiate between these two types of flowers. So what we will do is we will seek the help of an expert. So that is where the idea of supervised learning comes. So this expert is our supervisor who is going to tell us, okay, this group of flowers is Iris virginica, and this group of flower is the another kind. So the expert is going to help us to label these flowers. And what we need to do, since we are going to build a model that is going to operate inside a computer, so what we need to do is to come up with a method that can measure certain properties of these flowers so that we can make use of those properties to differentiate between these two types of flowers. So keep the discussion simple. Let's say that we decide on two properties. One is we will measure the petal length, another one is the sepal length. So those are, the petal area and sepal area, which will be obtained by multiplying these two numbers for petal and multiplying these two numbers for sepal. So we got these two measurements, and what we'll do is, so if we collected 100 flowers, then we will make these measurements on each of those 100 flowers. So as a result of these measurements, every flower now is a two-dimensional vector. That is, every flower is characterized by two numbers, petal area and sepal area. So what we can do is, since every flower is characterized by only two numbers, so we can take a graph paper and plot these flowers on that graph paper, because every flower is two numbers, so we got x-axis and we got y-axis. So we plot, let's say, sepal area on this side, petal area on this side. And versicolor flowers, we plot them using red ink, and Virginica flowers, we plot them using, let's say, blue ink. So basically, this is the plot of our training examples that we have done. Now, if you look at this plot, you can see that we can separate the two types of flowers by having a line drawn like this. That means in this particular case, this line is our model. And of course, one can write an equation for this line, and that becomes the mathematical model for our system. So basically, what we have done here is we have built and we have learned a classification model. So you might say, well, that sounds very simple, and why is then so much hoopla about machine learning? This seems to be a pretty simple thing to do. The problem is that for all real applications, you don't work in a two-dimensional space. You don't work with two features, but typically you work with 50 or 100 features. That means every object is characterized by 100 numbers. And there is no way you can do a visualization of objects in a 100-dimensional space. So what you need to do there is to make use of mathematical techniques. And that is where the difficulty of machine learning comes in. Anyway, let's continue with this example. So that's one model that one can build here. There is another possibility, and instead of building that simple linear model, one could actually say, well, I'm going to use this model as my classification model. Obviously, one cannot write an equation for this model because this is a highly nonlinear model, but one can come up with some kind of tree structure for representing this model. So that's where you will find a lot of people using decision trees to build machine learning models. So those will be built with boundaries like these. There is another possibility for the boundary, and one can say, well, I'm going to have this as my boundary. So you can see that compared to the two previous boundaries, this boundary is very, very complicated. But in this case, this boundary is able to separate all blue dots from all red dots. That means this boundary is not making any mistake or any error. So some of you might say, well, this seems to be the best boundary compared to the two earlier boundaries. But that is really not true, because this boundary is fitted particularly to this collection of data. But in practice, when you go and deploy your model, you might come across flowers which are a little different and get positioned a little differently on this graph paper. And in those cases, this boundary will not do well. So boundaries of this type are known as overfitted boundaries. And generally, one should avoid such boundaries. And this is what we call as model complexity. That is, if you are trying to build a model, you should try to avoid complex models. And a good design should be weighing off different trade-offs. So typically what people do is, if you start with a large collection of examples, you will divide that entire data set into 3 groups. One is the training set. That is where you will keep about 70% of your total examples. And this set is what you will do to build the model. Then you will keep another 20% of your data, and you will use this to test the accuracy of the model once the model has been built. And there is another 10% of the data that you will keep, and typically people call this as validation set. Generally what happens is that when people are building these models, there are a number of parameters that need to be set. So what one can do is one can make use of this validation set to figure out what is the best setting for those parameters. So if you follow these 3 partitions and use them appropriately, chances are that you will come up with a model which will work well when deployed in practice. Now, you might say, all right, we built a model. How do we differentiate, or how do we compare 2 different models? Or to put it another way, how do we measure the performance of a model? So basically, you can measure the performance of a model, especially when you're talking of classification, in terms of these 4 numbers. One is true positive. That is how many true positives are given by your model. What we mean by that is that your model is able to correctly identify the input as relevant. True negative, again, correctly identified as not relevant. False positive, made an incorrect label. False negative, missed an label. I think through these pictures, one can understand these better. So let us say that we have a system which is supposed to be looking at pictures and going to be identify whether a given picture is a picture of a cat or not. So if the system looks at this picture and says it's a picture of a cat, that means system has figured out a true positive. If the system says this is not a picture of cat, again, the system has figured out true negative. But if the system says this is not a picture of cat, that means it's making a mistake. So it's a false negative. If the system says this is a picture of a cat, again, it's making a mistake. So that's what we call as false positive. So what we will do is, once we have trained the system, we will feed these examples and figure out whether the system responded with a true positive, true negative, false positive, false negative. And based on those numbers, we can define the performance of the system. So the performance of the system can be given in terms of these 3 numbers, which we call as precision, recall, and accuracy. So precision is percentage of positive labels that are correct. And that's how we calculate the precision. That's how we calculate the recall. And that is how we calculate the accuracy. So basically, these are the performance metrics that people typically use to talk about their model. If you are working on a regression problem, then there is no question of false positive or false negative. There is a question of how far is your prediction away from true numbers, because you're trying to predict some numbers here. So in the regression model, the error is measured by taking the square of the difference between the predicted output value and the target value for your training examples. And you then add those numbers over all the examples to get an idea of how much error your system is making. So depending upon what kind of model you measure or model you build, you will define your performance. There is another term that you might come across, which is known as the bias and variance. So bias is what we call as expected difference between model's prediction and truth or ground truth. And variance is how much the model differs among training sets. For example, if you have multiple training sets, does the model produce similar results for all of them? Or if the results are not exactly identical, how much do they vary and so on? So basically, those are the factors that define whether your model is a high bias model, means model makes inaccurate predictions on training data. Low bias model means model makes accurate predictions on training data, and so on and so forth. Here is the final slide in terms of defining the characteristics or the performance of your model. And this slide is based on the principle of Occam's razor. The basic idea of this slide is that when you are faced with the problem of building a model or given a set of potential models, which one should you choose? The answer is go for the simplest explanation, because simplest explanation is usually the correct explanation. So don't get fascinated by complex models. If a simple model will do the job, then go for it. With that, now let's take a brief look at some of the model building algorithms. And again, we will look at these algorithms from two perspectives, supervised learning algorithms and unsupervised learning algorithms. Here is a list of some of the algorithms for supervised learning, starting with linear methods, which are the simplest methods, k-nearest neighbor classifier, neural networks, support vector machines, decision trees, ensemble methods. So these methods are all able to deal with problems that are more complex, that require non-linear solutions. While for linear problems, linear methods obviously are good methods. Now let me just give you some examples or illustrations of these different methods. So let's look at the illustration of KNN model, or let's call it with k equal to 1, the model is known as the nearest neighbor model. So look at this picture here. Blue dots are the examples from training set that we know are all of type Virginica. Red dots are all examples from the training set that we know are of the type versicolor. Here is a square dot here that represents a flower with two measurements, sepal area and petal area. Now we want to figure out whether this should be classified as Virginica or versicolor, whether we should color it red or color it blue. In this case, if you are using a nearest neighbor model, the idea is that look at the flower which is lying closest to this, and whatever is the color of that flower, choose that color for this example. So in this case, this is the closest. So basically, we'll say, all right, this should be colored red. But instead of doing 1 NN, if you do 3 NN, that is, instead of looking at just the nearest neighbor, you look at 3 nearest neighbors. Obviously, then in the 3 nearest neighbors, you have 2 blue flowers and 1 red flower. So you'll say, all right, this goes with blue because blues are in majority. So the idea of KNN model is very simple. It takes the unknown example, looks at its neighbors by calculating some kind of distance, and then it looks at k neighbors and finds out what is in majority among those k neighbors, and that majority decision is then taken as the label for this particular unknown example. So that's really how the KNN model works. It's a very simple model, does not require too much of model building, and can be implemented very easily. Here is another illustration of another kind of model, which we call as a decision tree model. So in this case, let us say that we have two measurements. In this case, the measurements are slightly different for illustration purposes. So it's the petal length and petal width. And these are the three types of flowers we have here now. All right. So basically what we can see here is that if we look at petal width values below 0.8, we see that all values below 0.8 belong to blue flowers. So basically we can run some kind of test here saying, is petal width less than or equal to 0.8? If the answer is yes, we don't need to do any more checking. We know it's a blue flower. If the answer is no, then we can look for, let's say, petal length about 4.75. So somewhere here is that value. And basically you can see that on one side you have most of the oranges, on the other side most of the green flowers. So basically we can run another test and do this separation. So one can build this kind of tree structure to perform your classification. And this structure is what we call as a decision tree model. And obviously, these are not created by manually looking at the data because we are working in a 10, 20, 50, 100 dimensional space. So there are techniques that will automatically generate a decision tree given data in a 50 dimensional or 100 dimensional space. So that's how the model will be built. In terms of unsupervised learning, these algorithms that are popular are k-means clustering, agglomerative clustering, self-organizing feature maps, recommendation system. So these are some of the examples. Let's look at the k-means clustering algorithm. Basically, in this case, k stands for the number of groups you want to do, and means means each group is represented by its center or its mean value. So essentially, as a user, you choose the number of clusters or number of groups you want to form. So you specify the value of k, and then you specify some random initial cluster centers. So in this case, as illustrated, we got all these black dots as our input data, and we choose 3 initial cluster centers, red, blue, and green. And we say we want to group this data into 3 groups. And what the k-means clustering will do is, it will basically refine these cluster centers in a progressive fashion such that these centers tend to represent well the 3 clusters. And finally, when the cluster centers stop moving, you will have your solution. So here is what it will do. It will basically assign data points to cluster centers based on how far they are from the center. So if you look at the initial centers and perform the assignment, this is what will be the result after one step. If you go through another step and another step and so on, you will find that ultimately the centers will move to the real centers for these different data points. And at that time, you will have your grouping result. And mathematically, this process, basically what it does is that it does some kind of optimization of this mathematical function. This is the most popular unsupervised learning technique. And there are a number of other ones. Here is an illustration of a technique known as the recommendation system. So in the case of recommendation system, there is a technique which people call as user-based filtering. So the idea is that you have a collection of users to whom you want to perform the recommendations. And obviously, you know about these users, that is, you have profile of every user in your database, or it's accessible to your system. So what your system can do is you can say, all right, let me compare this user with this user. And the system finds that these two users have a very similar profile. Then system will say, all right, this user liked this particular item. And since these two users have similar profile, chances are that this user will also like this particular item. So this is what we call as user-based filtering. A similar approach can be applied to what we call as item-based filtering. So we have a collection of items and we can say, all right, this item and this item are very similar. They have similar properties, similar attributes, and this item was liked by this user. Chances are now that this user will also like this item because this and this item are similar. So this is what we call as item-based filtering. So this is the kind of technique that Amazon or YouTube uses when they are suggesting to you the videos or the products that you are going to like. So this is an example of what we call as unsupervised learning. Just a simple cartoon to give you an idea of recommendation systems. All right, so that was about machine learning. So now let's come to deep learning. Why do we need deep learning and what's the difference between machine learning and deep learning? So what are the limitations of machine learning? The main limitation or the main idea in machine learning is that these machine learning methods operate on manually designed features. That is, those feature vectors that we talked about earlier, those feature vectors are generated by manually writing the code for generating each and every feature vector. And people have to figure out what features to use so that the system will be able to do the task that it is being designed for. And the design of such features, basically, if you are dealing with computer vision or speech understanding or natural language processing, the design of such features for these applications is extremely difficult. And that puts a limitation on the performance of the system. So in a typical machine learning approach, if you were building a system to differentiate, to figure out the objects present in pictures, then what you will do is you will input the picture, but you will come up with a design or with a set of features that you say, all right, these are the features that we need to extract from this picture. And once those features have been extracted, then you will go through that training phase that we saw earlier and build a system. Now, coming up with these features is really, really hard. And to give you an idea why it is hard, let's look at this picture here. What we are seeing here, as far as we are concerned, is a motorbike. But when the picture is taken and fed to the computer, is for this part of the picture, what the computer is seeing is a sequence of numbers. The computer is not seeing anything like this. Computer is seeing only these numbers. So the question is, this is what the computer is seeing, and this is what we are seeing. Or you can say this is a motorcycle that is a semantic concept, and here is a set of numbers. So the question is, how can we come up with a set of features that will take us from this set of numbers to this semantic concept? That is, how do we go from pixel values to a semantic concept? And how do we come up with features that will help us do that? That is really a very difficult task. It's not really easy to do. Not only that it's not easy to do, but there are other factors which complicate this. For example, when we look at these three pictures, we have no issue in saying, all right, they all represent the same face or the same person. But for a computer, this is going to be a very difficult task, because what has happened is that the camera viewpoint has changed. So you can design a set of features for a given viewpoint, but you can't really think of all potential viewpoints that might arise in future when the system is deployed. So what will happen is that your system will fail if it was designed only with one or two viewpoints in mind. And again, thinking of all potential viewpoints is really hard and not possible to do. So that's an issue, again, in terms of coming up with manually designed features. Another issue is that illumination. How a scene is illuminated, how is the lighting can make a big difference. So again, we need to figure out a way of how to tackle this issue. And again, manually coming up with solutions is not easy. Again, when we think of chairs, these are all possible chairs. So how do we come up with features that can actually handle all these possible variations in the concept of chair? Again, manually, it's not really possible. So what has happened is, or what the deep learning does is that it says, well, let's throw away the idea of manually designing the feature. Let us go for end-to-end learning. That is, let's throw pictures at the system and let the system figure out what features to use and how to differentiate between different classes of objects. So this is what we call as end-to-end learning. And in deep learning, to achieve this end-to-end learning, we feed raw data rather than feeding feature vectors to the system. So this is basically how deep learning is different from machine learning. That is, it takes over even the design of feature vectors, and that helps us to come up with better solutions. But this comes at a cost, because to build feature vectors, the system requires a tremendously large amount of training data. So deep learning is not a separate field, but it's a subfield of machine learning that has shown a remarkable success in dealing with applications that are particularly working with pictures, videos, speech, and text. Some of the characteristics of deep learning: extremely large amount of data is needed for training. It uses neural networks, and these neural networks are used with exceedingly large number of layers. Training time might run into weeks in many cases. And of course, it does end-to-end learning. That means no human design rules or features are used. Everything is learned by the system. So here is an example of a deep learning model, which is known as a convolutional neural network. And basically, such a network has a very large number of layers. Here is the input that we provide. And on the input side, we have a large number of convolutional layers, or you can say large number of filters. The parameters of those filters will be learned automatically. And then after some processing, the output of this stage goes to another set of filters, where again the parameters are learned automatically. That data is again passed on to another set of filters, another set of filters, another set of filters, and finally to some classifiers. And the whole process is automatic and everything is learned by itself. And this picture here at the bottom basically shows you the representations of the filters as they are learned by this system. So these networks or these kinds of networks have shown a lot of capabilities in terms of achieving great success for performing classification tasks. There's another kind of deep learning model which is known as the recurrent neural networks. In many cases, you are dealing with systems where the time component is also involved. If you are dealing with pictures, there is no time component. But instead of dealing with pictures, if you were to deal with video, or if you were to deal with speech, or if you were to deal with text, then there is a time component or a space component involved. And to deal with problems that involve time or space component, there is another set of neural network models that are suitable for that task, and that set is known as a recurrent neural network. So one will be building then such models if you are dealing with problems that do involve time component. Based on reinforcement learning, there are networks which are known as deep Q networks, and these networks then tend to learn without any external supervision other than by interacting with the environment in which these networks will be working. Here are some application examples of the success that these deep learning networks have achieved. Here is a picture, the output of a deep learning network, which is looking at a road scene and is able to color code different types of objects. For example, the blue one is referring to cars or automobiles. This one is the road surface. This is, the other objects on the side of the roads and all that. These are pedestrians that are out there. So these models are able to actually look around the environment and do the classification and label each and every object that's present in the scene. The recurrent neural networks, as I said, involve speech, text, and all that. So basically, these networks are being used to build cross-lingual conversation applications. That is, when you are talking, you might be talking in English. The other party might be understanding you through some kind of translation by a deep learning network, and they will respond in, let us say, in Gujarati, and then on the other side, the person will understand what you're saying in Gujarati, although the person may not know Gujarati. So again, that's the kind of application one can build and are being built actually using these kinds of networks. I think this slide does not have the changes because it's in the PDF format, not in the PowerPoint. But what this really was showing was this DQN network, how it's able to learn how to play this kind of game, which is known as the AlphaGo game, in a short period of time at the level of masters players for that game. Now, question is, how do we train these deep neural networks? So for convolutional neural networks, or for even recurrent neural network, the workhorse is what we call as the back propagation algorithm, which is really based on chain rule of differentiation, which you might have learned in your high school or intermediate class on calculus. So basically, it uses that chain rule of differentiation to come up with an optimization algorithm, which is known as the back propagation algorithm. And the training consists of optimizing some kind of a suitable loss function. And this optimization is done using a gradient descent technique, which is known as the stochastic gradient descent technique. And typically, this algorithm then tries to adjust millions of parameters of a network to achieve the performance. So in some sense, deep learning is really nothing but optimization. These deep learning networks are actually learning by doing optimization. Here are some examples of what people are able to do or achieve through deep learning. So this example shows you automatic description generation of images. That is, you can show to the network a large collection of pictures with the captions or description of what is in those pictures. And then after training, the network will be able to do on its own description of picture. So here is a picture, and this is the description that the network has generated on its own. There is another picture, and here is the description generated by the network. So you can see that network has achieved fairly good level of intelligence in some sense, and it's able to figure out what is being shown in a picture and is able to actually generate that description. There are a number of applications coming up in the area of medicine, where these systems are being used to do all kinds of predictions. For example, predicting whether a heart attack is going to be coming or not, and things of that nature. There are a number of chat interfaces that are being built using these networks so that when a customer goes to a website, he or she is not talking to an actual person, but he or she is chatting with a deep learning network without realizing that there is no human being on the other side, it's just a machine. So again, these are interfaces that are being built, and people seem to prefer these interfaces compared to the traditional interfaces. Now, some of the concepts of deep learning were known for a long time. The reason that deep learning became powerful and successful in last few years is because of number of reasons. Some of them are shown on this slide. Better hardware, large collection of examples on the internet, some technical changes in terms of some of the parameters that people were using for these neural networks. So many of these factors have actually given rise to successes in deep learning, and this is now a very well-established field. Now, as I mentioned earlier, the training time for deep learning runs into weeks for many, many applications. And obviously, not every company, not every organization can afford to do training in weeks. And also, to even do training in weeks, you need very powerful GPUs. And not only, you need actually a cluster of GPUs. So everybody cannot really afford all those things. So there is a trick which we call as transfer learning. And the idea of transfer learning is that these trained models that have been trained for a given task, what one can do is one can take these trained models and do a little bit of tinkering with them. And with that tinkering, you can actually make those models do a different task. That means you are making use of the knowledge that a trained model has learned for some other application, and you are then exploiting that knowledge for your application. And it turns out that the idea of transfer learning works pretty well, and it does give you faster training because you're not training from scratch, you're just doing some tinkering. And also, to do the tinkering, you don't need as much of data as you need it for training from scratch. So the data needs are low. So a lot of applications of deep learning are based on using the idea of transfer learning. Now, one thing that you might have read or might have come across deep learning, and especially nowadays, there's a lot of talk about ethics and bias in deep learning or bias in AI. So that's a very important issue and important concept. And let me just briefly mention what we mean by learning bias. And there is actually a pretty interesting story that goes back to 90s when when neural networks actually became very popular for the first time. At that time, the US government actually had a project that they funded to a number of companies, and these companies were basically building a system that could actually recognize tanks in the images. And when the demo time came, what happened is that these systems did not really work very well. They all failed. While when they were training them and building the models, they were all working very well. So when people started digging why these systems are not working at the time of demo, they realized that the weather pattern was actually playing an important role. The trained images were taken on cloudy days. So when they built the training, when they collected the training data, they basically collected images from days when the days were not sunny, it was all cloudy. And when they were doing the demo, it was a sunny day. And this difference in terms of overall illumination basically created a problem for the network, and the network was not able to actually do the recognition. So that's the idea of learning bias. That is, when you are collecting the data, make sure your data is representative of the environment where the system will be working. And in this case, they did not really take that into account. They just focused on few days of data, and it turned out that those days happened to be cloudy days. So the data really wasn't capturing the actual environment in which the system was supposed to work. So this is what we call as the learning bias. And this learning bias is showing up in number of situations nowadays. For example, people have trained face recognition systems, and it turns out that those systems were trained using training data that did not have pictures of people with dark skin. And as a result, when pictures of people with dark skin were presented to these systems failed to recognize them as persons. They kind of tagged them as gorillas or something like that. So again, that shows you the learning bias. That is, people were not careful in terms of selecting the examples. Interesting thing happened with the Microsoft when they built a chat system and they put it in the use. What the chat system started doing after a while was that when it was interacting with the users, and the users were using bad language, racism comments, and system started picking up that. So when the system was talking with later users, it basically was using that kind of language. So basically, the point is that you need to be careful in terms of what training data you select so that your system does not have bias. There are some other issues with the deep learning system that people are trying to overcome. Sometimes it turns out that these systems are not going to be performing well if there are some changes that are made to the input. For example, a system was trained to recognize numbers using black and white images of this type. But when somebody flips the background to white and white to black and inputs this image, the system does not recognize it. So there are issues in terms of some of the failures of deep learning systems, and people are exploiting these issues or weaknesses through what we call as adversarial attacks. So that's an area of deep learning that is currently under investigation. and a lot of progress is being made. There is another example of some of the shortcomings of deep learning system. That is, this input, the system is able to recognize this as a person. With this input also, the system is able to recognize as a person. So as you can see here, the difference between the two is that the locations of eyes and lips and all that are different. So what is happening is that the system is recognizing, okay, there are eyes, there are lips, there are things, but it is not taking into account their relative positions. So those are some of the drawbacks of these systems, which are being actually addressed right now by a number of researchers to trying to make them more robust. So just to summarize, what we have seen today is machine learning and deep learning are growing in their usage. Many of the ideas have been around for a long time, but are being put into practice now because of the technology progress. There are a number of open source software resources, R, RapidMiner, scikit-learn, PyTorch, TensorFlow, etc., that you can use to learn via experimentation. Plenty of data is there on the internet for you to download and experiment. Applications based on vision, speech, and natural language processing are excellent candidates for deep learning. And of course, one need to apply filter. One need to filter hype from reality. That is, if you look into the literature, look into reports, shows, and all that, everybody's hyping and saying, okay, you know, AI is going to do this, AI is going to do that in next few years, this is what's going to happen and all that. I just want to say that we need to be patient, we need to cut out the hype, and we need to remember this statement from 1965 given by Nobel laureate Herbert Simon. In 65, people were claiming machines will be capable within 20 years of doing any work that a man can do. And we have come about 50, 60 years from that, and still we have not yet reached there. So point is just separate the hype from reality. There are nice things about machine learning, there are nice things about deep learning, and one can get a lot of things done, but don't believe, don't hype, or don't believe everything that you hear about these systems. So with that, I will stop here, and I am open for any question anybody might have. Thank you for listening.
Thank you, sir, for such basic and very informative session for the machine learning and the deep learning introductions. So audience, if you have any questions, you can just ask.
Generally, I don't get any questions, so I'll be surprised if there will be some questions.
It was really a nice walkthrough from ML to deep learning, sir. I have just one sort of query. The query is that you see, possibly people or many researchers are using the DNN technique very blindly to almost all the problems. Is it a good idea, or we have to have some kind of consensus decision that, okay, these are the problems which could be solved by conventional machine learning problem, and for this kind of a problem, let us use DNN?
I think you raise a very good point. Let me mention a few things here. See, every year when I'm teaching, I give a project. And one of the projects has a training data such that there are 90% of the examples in the training data are from class one type, and the 10% of the examples are from another type. And with sklearn and number of other software packages and source code available at different GitHubs and all that, so people are able to actually do all kinds of things without really understanding what they're doing. And then the students come back and say, oh, I got a fantastic result. I said, what did you get? Oh, I'm getting 90% performance. And I say, all right, that's great, but what's the performance on class 2, which is 10% in your data? Oh, that's, it's not able to recognize, but I'm able to recognize the rest of it. So the point is that so much of the software, so much of the data has been made so easily available that people basically lose sight of the underlying concepts, and they simply run the software or the program, throw the data at it, and get the results and say, oh, I know machine learning, I know now deep learning. That's really not the same. Now, coming to what applications are suitable for what. See, the machine learning, as I said, is good, and you can use all kinds of even nonlinear models. But machine learning is useful when you can come up with your own feature vectors. If you are working in a problem that involves cognitive aspects, for example, we look at pictures or we hear something and try to make decisions, those are the problems where it is very difficult for us to say how we are able to understand something. We can't really come up with, oh, these are the things through which we are understanding. So anything that involves vision, involves speech processing, involves natural language processing, those are the application areas which are really good for deep learning. Anything else, actually, you can do it very well with machine learning. But the point is, people are also, trying to do the fashion. So if deep learning is in fashion, then everybody is going to do deep learning, whether deep learning is really needed or not. So I hope I answered your question.
Suman sir.
Yes, yes. Thank you very much for your answer. I think
Thank you, sir.
all of us will be benefited out of your lecture and your answers.
So this is one small memento from our side, from the IEEE SPS Gujarat chapter, IEEE Gujarat section, and the Dhirubhai Ambani Institute, Gandhinagar. So please accept it.
Thank you.
Okay. Now I request to all participants, please open your camera so we can take one session photograph.